Welcome to the Financial Math lesson, part 1 on loans. In this lesson, I'm going to talk about the amortization of loans, basically mortgages, and balloon loans. There'll be a second part to this lesson also. Amortization refers to the distribution of payments into multiple equal installments where each payment consists of principal and interest. So, for example, on a house loan, or mortgage, I should say, as you may be aware, same thing with a car loan. It's the same amount, and it's divided between some of that amount is principal and some of it is interest, and that'll vary over the course of the payments. We'll see some examples of that. Let me point to where I'm at here. So repayments are divided in equal amounts for the duration of the loan. I just said that. However, the amount of interest and principal payback in each installment varies, and we'll see that in an example that follows. This process is known as the equated monthly installment, EMI. And then there's a terminology issue here. I'm using the term payment, although technically it's a repayment of money that has been previously loaned, but since payment is more commonly used in the literature, we'll use the word payment. Then here are some of the attributes that we'll be using. P is for the principal, that's the amount borrowed. A is the equal periodic payment or repayment. I is the interest rate per compounding period, and N is the total number of payment periods. It is assumed that the compounding and payment periods coincide. We saw earlier where these could be different, and it led to some more complicated analysis, but we're not going to do that for the mortgages and loans here. When doing the calculation, it's important to note that the loanee, the person who receives the loan, must pay back the amount of interest due at the end of each payment period. And then whatever else remains in terms of the payment, A, would go into repaying the principal. So let's look at some of the formulas on this following slides, and as well as an example. Well, on this slide and the next, I'm going to derive the formula for A, the amount of money due at the end of each period. And the way we'll do that is by looking at the balance at the end of each period. So we'll start with the balance at the end of the first period. So it's the principal plus the accrued interest to the principal, so you owe this much, but then you paid back A. We don't know what that is yet. We want to solve for that. And so we have this equation for the amount still due, the balance, so to speak, at the end of the first period, and we can write it this way. Then the balance at the end of the second period is just B1 plus the interest on B1, so this expression here, and then minus your second payment, which again is A. So we don't need to put any subscripts on A since it's the same amount. And then you just plug in this here for B1, and you get this. Then B3, the balance at the end of the third period, is 1 plus I times B2 minus A. Again, you plug in B2 here, and you get this expression, and then the pattern is clear at the after the kth period. It's 1 plus IK times P minus, and I just factored the A out of this here, minus A times this expression here. And then we know also at the end of N periods, where N is the total number of periods in your mortgage or loan, that has to be 0. So we also have that B sub N is 0. And then on the other hand, we know B sub N follows this formula here, just plugging in N for K. We have this. And then we can just have 0 equal to this. And we can bring this minus A times all this to the other side. And we have this here. And then let me finish this off. But you can see now that we've isolated A. We just need to get an expression for this and then divide it into this side here. and then we'll have our solution for A, which I'll show you on the next slide. Okay, so let's finish up our problem. I'm going to use the formula for the sum of a finite geometric series. We derived this in the very first lesson on progression, so you may have forgotten by now, but we're going to need this a few times. So I'll remind you once here, but then I'll count on you keeping this in mind as this comes up again. So for our problem, little a and small a are the equated, and then r is just 1 plus I. We plug that into the formula here. We get this here. Then the minus 1 and the 1 cancel, and you just get this over 1. Then you multiply both sides by 1, divided by 1 plus I to the n minus 1, basically the reciprocal of this. And you get this expression here. And if you divide top and bottom by 1 plus I to the n, you get it in this format here. I make a note here that this formula is equivalent to the formula for regular payments from an ordinary simple certain annuity, which I copied up here just to remind you. This was from the annuities lesson number 1 that I did a few lessons back. And you can see the structure is exactly the same. The amount paid back for the mortgage or loan is A, and that's equivalent to the amount you're getting paid from the annuity, and then the principal on the loan is similar to the amount of money that you paid to buy the annuity. It's the same idea. You could think of the bank as buying an annuity from an individual who then pays them back equal amounts over a period of time. We don't call it that, but that's the idea. So it's the same things, but with different terminology. Each payment is a combination of principal payback and interest payment where the sum of the two is equal to A. Remember, A remains constant. However, the ratio of principal payback to interest payment changes over time, and we'll see that in an example. At the end of each payment period, the interest owed is I times the amount of outstanding balance at the beginning of the period. Thus, the interest owed at the end of the period, K, is given by the following formula. So that's just saying here, if you want to know the interest to be paid at the end of period K, you take the balance at the end of period K minus 1, or at the beginning of period K, and you multiply that times I. That's what we've done here. And then I've just plugged in our formula for B, so K minus 1 to get this here. And so that we can also compute the amount of principal that's repaid. That would just be A minus this number here, since R, we call this R sub K, the amount of principal repayment. Since R sub K plus I sub K has to equal A. Again, the A remains constant, but I sub K and R sub K vary over the course of the repayment schedule. We can also write I sub K recursively, and that's convenient for programming. And I've actually done a couple of programs in support of this lesson, which I'll discuss towards the end of this lesson, which make use of this formula as well as some of the other formulas. So let's see how we get that. We take our formula for B sub K minus 1 that we derived a few slides back. We derived it for B sub K, but we'll just put in K minus 1, so you would have a K minus 2 here. Then you multiply both sides by I, and you notice this is our capital I sub K, and then this I sub B sub K minus 2 is capital I sub K minus 1, and you get this recursive formula. So you can, once you compute A, then this you can compute the first one of these interest payments. That gives you the second one, and so on. You can do this recursively. Okay, so let's look at an example on the next slide. So our example is a car loan for 3 years at 3% annual interest rate, and it's paid back monthly. So we'll use our formula for A that we derived earlier on in this lesson. With P equal to 10,000, we need to compute the monthly rate, so it's 3%, which we convert to a decimal, 0.03 divided by 12, and we get 0.0025. And then the number of periods is 3 times 12, or 36. And we plug that into our formula, and we get the monthly payment is $290.81. A breakdown of this interest versus principal repayment for the first 4 payments I'll have in the table in the next slide. Given the relatively short term of the loan, the principal payments outweigh the interest payments from the start. However, for longer loans like the home mortgages, for example, a 30-year mortgage, typically the interest payments are greater than the principal repayment at the beginning of the loan. And then that changes as you go over the 30-year period, where towards the end you're paying back more principal than interest. So let's look at the table in the next slide. So here's the breakdown for the first 4 payments. I copied A from the previous slide, so we have that to compare. And then we're using our formula, the recursive version of it, to compute how much interest is paid for the first period. It's 25. That's easy. You can do that in your head because it's 0.0025 times 10,000. And then you just subtract that from A to get how much of the principal is being paid back. And you can see you're paying back a lot more principal than the amount of interest. And then you have a little bit less balance at the end of the first period, so the interest to be paid is a little bit less, and the principal paid back is a little bit more, and that pattern continues with the interest getting less and the principal payment getting a bit more. So I have a program that'll do this for you, and it'll print it out to a spreadsheet, the entire breakdown. In this case, you would have 36 lines, and you can study the pattern of interest versus principal payback. It may be desirable to round upward or downward the periodic mortgage payments to the next dollar, $10 or $100 value, just as some examples. And you could round it up $50 or whatever. The algorithm for doing that is shown here on this slide, and then I'll give you an example on the next slide. So first you determine the periodic payment, A. We have the formula for that. Round up A to the next whatever is convenient. So for example, if somebody has, $1,473 payment, maybe they request, could you just make it an even number for me, 1,500, just as an example. So you would round it up to the next 100 in that case. And then the computations are in this step here. We compute the penultimate, in other words, one before the last balance, so Bn minus 1, assuming that the A hat, the rounded up number, is used. And then we just reuse our formula, except we put in A hat here instead of A. And so this is how much is still left at the balance when you have one more payment to go. And then when you need to pay in the very last payment, it would be this amount here, how much is left in the balance, and then the interest over that last period. So that's how much that you would need to pay on the adjusted last payment. And I had a note here, one could go directly to step 4, since we know the formula for Bn minus 1, or we could take, we could just stop at step 3 and then multiply by 1 plus I, which gives you the same thing as this here. So let's see what that looks like in an example. As an example of rounding up or down, consider a $200,000 mortgage at 6% annual interest with payments due each month. Determine the mortgage is 10 years. So the first step was we convert the 6% to a monthly interest rate. So we take 0.06 divided by 12 and we get 0.005. Then we use, let me point here, then we use our formula from a few slides back to compute the monthly payment without any rounding. And then we round it, let's say, just to the next dollar. So we're going to pay $22.21 just to avoid having cents in our monthly payments. And then we use the formula from step 4 on the previous slide to compute the final payment. We plug in the A hat instead of A here, and we get 21.24.32. So that's less than A, which is expected since you were paying a little bit more all the way along, and so the last payment is slightly less than this. And we can change it around. We can round to the nearest $10. So instead of this number here for A hat, we'll just do 22.20. Again, use the same formula here, where the only difference is we have 22.20 plugged in here, and we get 22.87.20. And since here we're paying a little bit less each month, you would expect that the final payment would be a little bit more, which it is here, right? It's 22.87, which is a little bit more than A, since you were paying slightly less each month. And then we can do it to the nearest 100. So we'll just pay $2,200 a month instead of $22.20 and 41 cents. And put that into the formula. I just double checked it, and it's a little bit surprising, even though you're paying only $20.41 less a month, your final payment is quite a bit more. It accumulates quite a bit, even though that you're just paying a little bit less in your monthly payment. Okay, so in terms of rounding down, keep in mind that the loanee is expected to pay at least the amount of interest owed each period. So you can only drop down so much before you violate the agreement. And rounding up, you have a different issue. You may actually have zero for not just your last payment, for several payments. So for example, if we did, instead of $22.20 and 41 cents, we decided to pay $3,000 a month, and almost for sure you're going to miss several of the last payments. You're not going to need to miss, in the sense of you're going to have the loan paid off before that. So keep that in mind also. In a previous lesson, I think it was the second lesson when I talked about simple interest, we had an example of a balloon loan. In that example, payment of all principal was deferred until the last payment. So we only paid interest along the way, and then the entire amount of principal was paid at the end. That was the balloon. We'll call that B, that amount B. In our initial example, B was equal to P, the principal, but it doesn't have to be. You could pay off some of the principal along the way, P minus B, and then you would pay B at the very end. So let's look at the derivation of A in that case. So we have our variables as we've defined them before: A, P, the principal, B sub n, the balance at the end of step N, I, the interest rate per period, and as I said, B is the balloon, the amount of principal that you pay at the very end, which could either be zero or all of P. If it's zero, it just reverts back to the formulas we have for the car loan and mortgages. So relying on the previous derivation, we know that the B sub n, the balance at the very end, is given by this formula here. And when we did the mortgage calculation, that was equal to zero, but now it's going to be equal to B, this balloon that we pay at the very end. And then these next few steps, I'm just isolating A. First, I wrote this in terms of the finite geometric series. Then I took this term and added it to the left. I took the B and subtracted it from the right. Then I multiplied by the reciprocal, and we got this here. And we have a little bit more calculations to do, which I'll show you on the next slide, and then I'll do an example. I carried over the formula from the end of the last slide, and now I want to solve for P, given that we know A, I, B, and N, so we're kind of working in reverse here. And what you do is you multiply the denominator times A, then you add IB to both sides, and you get this here, and then you divide both sides by I times 1 plus I to the N, and you get this formula for P. And if you like, you can divide the denominator into each one of these terms, and you get this expression here. If B equals 0, the formula for A is the same as for the non-balloon case, where you have a mortgage or a car loan. So I mentioned this already. And if B equals P, so if you plug in P here for B, all the principal is paid at the end of the term. So at the end of each period, the full amount of principal is still remaining, which means that the A would be I times P, which is borne out by just working through this formula here. And so you get this from just factoring out IP, and then on the top you have IP times 1 plus I to the N minus 1, and that cancels with the denominator, and you get IP. So that's what's to be expected. Then there's some variants of the formula for A. The way we derived it, the last payment A and the balloon payment were at the same time. You can have a variant where you make N payments of A, and then you have one more period N plus 1, where you pay the amount B. In that case, the B, the balloon, would be the balance at the end of period N plus the interest over the N plus 1 period, and you would get this here. And then when you solve for A, plugging in the formula for B sub N here, which I didn't go through the details, but you would get this different formula. So this is basically by extending out one more period and paying the balloon at that very last period. So that's another approach. Now on the next slide, I'm going to give an example, but I'm going to use the initial approach we talked about and not this variant here. So let's look at an example. A car loan stipulates payments of $500 at the end of each quarter for 5 years, with an additional payment, the balloon payment, $7,000 at the end of 5 years. What is the present value of the loan? At 6% nominal annual interest, compounded monthly. So the monthly interest rate is 0.06 divided by 12, or 0.005. And we want to convert that into an equivalent quarterly rate, and we had the formula for that from before. It's given by this here. So we just plug in our numbers, and we get the equivalent quarterly rate, 0.015075125. And remember from the previous lesson where I cautioned this about truncating, you want to keep a large number of decimal places here, so you don't have, especially when you're raising something to high powers, so you don't have any rounding issues. So again, we're essentially being asked to work backwards. This was our formula for P, the initial amount of the loan. That's basically what we're being asked to find. Again, we're given A, it's our 500. We computed J, the interest rate per month, the balloon amount B, and the number of payments, 20, right? It was 5 years and quarterly. These payments are being made quarterly. So we have 20 payments. This is our formula from the previous slide, except we're using J now because we had to convert the rate. Then we just plug in the numbers and we get 13,767.57 So that would be the amount of the loan. And if you paid $500 a month under these rate conditions, that would leave you with $7,000 to pay at the end of the balloon. Okay, so I have a couple of Python programs that I wrote to help with the calculations, and I'll describe the GUIs, the graphical user interface, on the next few slides, and I'll make the programs available to you on the same GitHub directory that I've mentioned previously, but I'll put the link again in the information to this video. We have two programs in support of this lesson. The first one is about amortizations, and this is the name of the file. And again, I'll give you the link to the GitHub directory that has this. And this does three things. It calculates mortgage payments, so whatever the monthly or whatever periodic payment. And then you can also tell it how much you can afford per period, and it'll tell you what the maximum amount of loan or car loan or mortgage that you can afford. And then there's another pane to this application, and that calculates where you make early payments in principal. So you pay a little bit more or a lot more principal on a regular basis from some point out, and it'll calculate the how much sooner your loan is going to be complete. Then the second program is on balloon loans, and that calculator is used to compute either regular payments for a balloon loan or the present value of a balloon loan given the amount of regular payments. And I'll give you some examples in the following slides as to how to make use of the user interface. So let's look at an example using this amortization calculator. There's two parts to it. I'm showing you the left-hand side of the GUI, the user interface, and then I'll show you an example of the other aspect later. So let's take a loan of $500,000, 4.5% annual interest, 12 payments per year, and 25 years. Okay, then you can compute the periodic payments, so how much you have to pay back every month in this case. That's this number here. And then you can hit this button down here, and this will give you the payments over 25 years in terms of the breakdown, I should say, in terms of how much interest you're paying and how much principal you're paying. And it gets sent to a spreadsheet. And the file is listed down here. It's usually a file wherever you have the program that you're running, that same directory, and this is the name of the file. If I cleared this and ran it again with a different example, and I didn't delete breakdown_1, the program was designed to create another file called breakdown_2, and so on. So you can keep using this without having to go into your directory and delete the files. You just need to keep track of which one of these CFV files is corresponding to the example you're doing. And then there's another aspect of this which I'll also demonstrate here. So we'll do a clear, and we'll come back, and we won't put in the amount of loan, but we want to figure out how much we can afford given the conditions. Let's say they're the same. So the interest rate is the same. 12 payments, 25 years, and let's say that we can afford more. Let's say we can actually come up with $3,000 per month in this case, and we want to know what's the maximum loan that we can afford under these conditions. So it should be more than the $500,000 because I put a bigger number than what we did in the previous calculation. And in that case, you leave this blank, and then you use this button here. And you can see here, given this slightly larger amount of contribution you can make per month, you can afford a larger mortgage. Okay, so that's the first aspect of this calculator. I'll show you the other aspect in a second example. This is an example of the breakdown file that I mentioned, and it's for the particular example that we ran for the 25 years, 4.5% annual, 12 payments a year. And since there would be 300 lines, I couldn't fit it on one slide, so I just showed you part of the file. I showed you the first 10 periods and then the last 10. So you can see here the payments, the mortgage payments are the same throughout, but the interest and principal is different. You start out at $1,875 paid in interest, and then this much principal is being paid back. And you notice as the balance goes down from your initial $500,000, the interest payment, of course, gets less and less and less, and it's almost nothing at the end. But your principal that you're paying back gets larger and larger as you go through the course of the loan, and then eventually the balance is zero. That's when you've paid everything off. So this is the same calculator. Now I'm showing you the entire user interface. Before I was just showing you this left side. What this does is it allows you at some point in the loan repayment to pay off additional principal, a certain amount every period until the end of the loan. So we can do an example just to show you how this would work. Let's say we have a $300,000 loan at 4% and 12 payments a year, and the loan is 30 years. Then you come over here, and let's say after 10 years, which would be 120 periods, 120, you get a better job, and maybe your spouse gets a better job, and so now you can afford to pay off the principal sooner. So you want to put in an extra $1,000 every period, in this case every month, and you want to know how much sooner the loan is going to get paid off if you do that. Clearly it's not going to be 30 years anymore. So that's what this button will do for you. So it shows you these were the regular payments for the first 10 years, and this was the balance after your 10 years. So you still had $236,000 and some odd amount. And then now you want to pay another $1,000. So you notice here, this number is just $1,000 more than that. So now you're, for the period 121 and so on, you're paying this larger amount. And then this calculator does a calculation. It says that you're going to pay the loan off in another, you need to round this up, another 118 periods. And so the total number of payments would be 238, which this is also calculating. It normally would have been 360 because it was 30 years, 12 payments a year. So you're basically short, or you have 122 payments fewer because of this additional amount. And then it also calculates the original total interest was this amount, and now given that you're paying off the principal sooner, the total interest is this amount, and it shows you here that how much you saved. So it's quite good. You're saving close to $58,000. If you click this button down here, it'll show you the breakdown similar to what we had for the previous breakdown, except now it'll show you for the first 120 periods, it'll look just like what we had before, but then after that it'll show the adjustment where you're paying the additional $1,000 a month, and then it'll follow through all the way until the last payment here, payment number 238. And that'll also put it in the same directory from wherever you've executed this program. And the file is given this name here. Okay, so that's one option. Then there's another option where you want to find out how much money you need to contribute in order to pay off the loan after a given number of periods. And we can do an example of that. So let me clear this. So again, we have 300,000, 4%, 12, 30 years. And let's say it's the same thing here, except now instead of putting in this additional amount, we want to find out what that might be if we want to pay off the loan and say 250, or so let's say 260. So basically 100 payments less than if we had just stuck with the initial payments. And then here you would click this button here, and that does the calculation. So you want to, again, it's the way we've put the number in here, it would of course be 100 periods less, and it's giving you the additional amount that you would need to pay. So it would be $683.19. So if you paid that much more, you would get done after 260 periods. Then it also does the total interest from the original loan, the new interest, total amount of new interest, given this arrangement where you're paying an additional $683.19, starting with the 121st period. And so you would save over $47,000 in this case. Okay, so that's it. But I'll also show you the breakdown spreadsheet, or at least part of it, for the first example I did. I'll do that on the next slide. This is the part of the spreadsheet, I should say, that's the output from the first of the two examples I just talked about on the previous slide. It shows you the breakdown of payment, interest, and principal, and then the remaining balance. And so you start off with paying this amount from our calculation for A, the fixed amount that you pay in this case, every month. And you notice the periods are numbered here on the left. And the reason I gave this middle thing here is that this is where we adjusted the payment. We added $1,000, if you recall, and that was after period 120, the next month, we added 1,000, and it remained at that amount. And so we were paying off the principal more quickly in that case, because all this additional $1,000 went to paying off the principal. So you can see here that we jumped from paying $642 to $1,644 in the principal. And then this is showing the balance here. And there's this little marker that just shows when you're going from the regular without that additional principal pay down and then the extra amount. And that goes all the way to the end. But since the number of periods no longer evenly matches where you get zero at the end, you kind of have this odd period. The last period's a little bit less than this here in order to get this down to zero. And that's why I listed that as an adjustment. Okay, so that's it for this lesson. But I have a second lesson on loans, and I actually have some more Python programs to go along with that. So I'll be posting that video once I get it completed.